All right, this is 2-3 pre-calculus, expand binomials using the binomial theorem. Don't make me take marbles away. I'm opening them up for people that are talking over me. There were 4 people that I counted that talked over me. Let's count. 1, 2, 3, 4, 5 now because Aurelio also talked over me. All right, don't let me take any more marbles away. Here we go. Question, yes, Aurelio. Ellery, lost your class another marble. Beverly, lost your class another marble.
Excuse me.
All right, so our objective today is to do what with a quiet raised hand? Jaden. No, that's not how it works. You can look at your own paper too. There it is. So we've done these problems before where I have a plus b to the power of 2. That's just a perfect square. Square the first, double the product, square the last, we're done. We've done that before. Now we're going to do something a little bit harder. We're going to go to the power of 4, the power of 3, 5, and 6. I'm not going to do anything above 6 because that's just tedious and that's kind of like pointless. But you should be able to do them. If I give you a power of 10, you should know the procedure behind it. So maybe a question on the test or quiz might be, explain the process if I had something to the power of 10. I won't ever make you do the math because, again, that's just kind of cruel. So where does it come from? We're analyzing patterns for the first half of the lesson. Second half of the lesson is applying those patterns, those rules that we've discovered. So first, a plus b squared. And again, a and b can be anything. A could represent negative 5x squared. B could be 29x. They can represent anything. I'm keeping it as general as possible so that you guys can, 1, pick up patterns easier, and 2, apply it to any problem that you see. So one thing I will say that will be confusing in the future is be careful about negatives. When b is a negative, it's still a plus in between, and then you have to either square or cube that negative correctly. So just be wary of negatives in your future. Here we go. A plus b squared is the same thing as a plus b times a plus b. Nod your heads. Yes, I agree with that statement. We're all nodding our heads, right? Okay. So I'm going to go ahead and set up my general rectangle, a plus b, a plus b. I'm going to multiply those. I'm going to get some rapid fire volunteers here. I'm going to do the column times row. I said which is both of them together. I don't know. Row times column. A times a is what? Quiet raised hand. Ellery. A squared. Everyone is writing it down with me. A squared. A times b. Oscar. Not a plus. You're going to multiply them. A times b is a times b. Yeah, just ab. B times a. Beverly. Yeah, b times a. And you can also say that it's a times b again. ab again. Yep. And then b times b. Sam. B squared. And then we add them all together and we get a squared plus 2ab plus b squared. And that, again, is the same rule as square the first, double the product, square the last, put that baby to sleep. Side note, has anyone seen Stephanie with the baby in her arms? I saw her second period. Pretty cute. No? Ask her next time that you see her in the Zoom meeting, if you ever see her in a Zoom meeting. All right, so now we're going to go ahead and multiply out a plus b to the power of 3. I'm going to increase this into our objective. I need to have this power up here, this n, 3, 4, 5, 6. I'm now there to the power of 3. And this is the reason why it's so hard, because in order to find that, I first have to find a plus b to the power of 2, and then also multiply another a plus b, which means a plus b to the power of 10 is a plus b times a plus b times a plus b times a plus b. I have to have a mega giant rectangle. And I'm hopefully finding that there is a quicker way. So what do we do here? Well, we take a plus b squared. We know that a plus b squared is a squared plus 2ab plus b squared. So I'm going to multiply a plus b times a squared plus 2ab plus b squared. Again, I'm hoping that everyone can follow along. This a plus b squared is that top. This a plus b on the left is on the left of our general rectangle. And then I multiply again. More rapid fire volunteers. The top left, a times a squared is what? Chewy. It is indeed a cubed. What about a times 2ab? Oscar.
It'd be 3a.
That's not 3. So when you multiply all the coefficients. So 2 times 1 is still 2. And then how many a terms do I have now, though?
2ab.
So it's not ab. I have 2 of those a's. So it's a to the power of
Squared.
a squared. Yeah. So our answer is 2a squared b. All right, we're going to keep going through this. Next, I have b squared times a. Beverly. AB squared, exactly. Remember, the exponent represents how many of that variable I have. Over here, I have 3 a's, I have 2 a's, I have 1 a, and I have 2 b's. The exponent, Jaden, represents how many there are. All right, next cell, a squared times b is what, Sam? Careful, so there's only 1 b, so it should just be a normal b, right? And how many a's are there? A squared b, perfect. All right. Jaden, do the next one. 2ab times b. 2ab times b is what? 2abb, exactly. And then b times b is? B to the power of? Yes. You need to simplify this. B times b is? Yeah, thank you, Drew. B squared, thank you, Jaden. B squared. So it's 2ab squared. And then finally, last one, b squared times b. Aurelio, go for it. B cubed, exactly. Again, I add these all up. I'm adding like terms, and you have to be careful about your like terms. They have to have the exact same exponents. And typically, the way that I write my variables is in alphabetical order, so I don't get confused. I don't want to say ba squared. It's mathematically correct, but it's confusing. So I'm going to start with my a cubed term. So I'm going to say this is going to be a cubed plus, let's do all of our a squared b terms. I have 2 of them, 2 a squared b's, another 1 a squared b. We have a total of 3 of those a squared b's. So plus 3 a squared b's. How many of these ab squareds do we have? Ab squared, I have 1 of them there. I have another 2 ab squared for a total of 3 of those ab squares. So plus another 3 ab squares. And then there's only 1 of those b cubed, so plus b cubed. Whew, all right. Let's try, okay, so what we've just done, a plus b to the power of 3 is this. And hopefully you should start be worried right now. Wait, we have to memorize this? We have to memorize that? We have to memorize the power 4? We have to memorize the power 5? Kind of, yeah. But there is a shortcut, and I will be getting to that. In general, that is the form. And I want you to start looking for patterns, especially when we finish doing a plus b to the power 4. And if I was a cruel math teacher, I would make you do these all the way out through 6, since that's our objective. But you'll see once we hit 4, it gets really, really hard and tedious. So let's try that last hard and tedious problem. Again, a to the power, or a plus b to the power 4. That's another a plus b times our old a plus b to the power 3. This old a plus b to the power 3, I'm going to put that on the top of our general rectangle. So label these 4 spots, a cubed plus 3a squared b plus 3ab squared plus b cubed. Did you get the notes?
Yeah, a lot of
Yeah, go for it. So I have a cubed plus 3a squared b plus 3ab squared plus b cubed. Whew. And this is only to the power 4. We have to get all the way up to the power 6. And in theory, to any power. We're finding a pattern that works for any power. All right, rapid fire again. Here we go. Nice and easy one to begin us off. So a to the power of 3 times a, Beverly. A to the power of 4. Next one, we have 3a squared b times a. Oscar.
It'd be 3a cubed.
3a cubed b. There it is. Thank you. Next one, 3ab squared times a is what? Sam. There it is. A squared b squared. You guys are really getting the hang of this. Good job. A times b to the power of 3. A times b cubed is what? Oscar.
B to the power of 4.
Ooh, careful. This is not a b. This is just an a.
Oh, it's the a b cubed.
AB cubed. There it is. Next, a to the power of 3 times b. Go for it, Jaden. Yep, there it is. B8 to 3. And I'm going to write it in alphabetical order, but you're correct. A to the power of 3b. Nice. Next one. 3a squared b times b. I'm not going to call on Leo until he catches up with the notes. Someone else. Ellery, I haven't heard from you in a while. What's 3a squared b times b? 3a squared b cubed. Close. There's two of those b terms, right? Yeah, so b squared. Do the next one too. Can you do the next one then? 3ab cubed. There it is. And finally, last and easiest, Mr. Sandell do b to the power of 4. Again, you need to add all the like terms, and hopefully you're seeing this pattern now that these diagonals are always going to be like terms. Diagonal is going to be a like term. That diagonal is going to be a like term. What color do I have next? I have black. That diagonal is going to be a like term. Those are all of our like terms. So if I write this all out, this answer over here is equal to a to the power of 4 plus 4 a to the power of, ooh, got weird lag, a to the power of 3b plus 6 a squared b squared plus 4 ab cubed, and then finally plus b fourth, plus b to the 4th. I want you to start looking for patterns. That's the whole point of us doing this. One, to show you it's hard and we need a shortcut. Second, we need to find the patterns so that we can find the shortcut. Once you guys find the shortcut, you've unlocked it. You can use that shortcut from here on out. I won't make you do all this hard math again, unless you want to. What are the patterns? Look between our first a plus b squared, look to our a plus b cubed, look to our a plus b to the power of 4. What patterns do you see? And to help you narrow your focus, ignore the coefficients. Ignore this too. Ignore all the numbers that you see that are coefficients. The powers I want you to pay attention to. This is the power of 2, goes to the power of 1, a is gone. B, not a b, b to the power of 1, b to the power of 2. What do you notice? What do you see? I'll give you guys 2 minutes to really think about this. All right, Jaden, what is the pattern that you and your group found?
So we noticed this is like slowly kind of like just dipping until it's gone, right? And then this is like the opposite. It's like 3.
Yeah, use this black one over here.
This one?
Yeah.
And like here's B, it's like nothing. And it's B to the 2, it's B to the 3, it's B to the 4. And then yeah, it's like the same with the A's. 4, the 3, the 2, and
All right, so thank you. Thank you. This is officially going to be called Jaden's pattern. Using Jaden's pattern, someone else that wasn't in this group explained, using that pattern, what is a plus b to the power of 5 going to look like? If I have a plus b to the power of 5, I don't know what the coefficients are. Again, I told you guys to ignore those. Ignore the coefficients. What should it be? Let's talk about the A's. What should A start with? Ellery? Then? It goes all the way until it disappears. A to the power of 0 means it disappeared, right? I'm gonna get someone to do the B's if that's okay. Someone explain the B's with Jaden's pattern. Beverly. Starts off with just B. B squared. B cubed. B to the fourth. B to the fifth, and then finally. Wait a second.
Well, you would actually start off with like 0.
Oh, 0, then 1, then 2, then 3, then 4, and then 5. And that matches up because you guys, your group found that the first and last term have to be the 5. 5 and 5. And now we're. All right, everyone right now, give me a fist of 5. How well do you understand Jaden's pattern? How well do you understand Jaden's pattern? Fist of 5.
What?
Whoa.
You help sure.
That's not.
I said if you help use. I did say that. I said it was 15.
Sure.
You guys just have nasty ears. Whoa.
All right, so I want to show the second pattern. You guys are halfway there. Half of the battle is figuring out that it's descending powers for the first variable, starting with our original n value, and then the second variable ascends, so it goes from 0 to 1 to 2. Here's the second pattern. The second pattern is the coefficients. So my question for you is, where do the coefficients come from? Why do we go 1, then 2, then 1? Why do we go 1, 3, 3, 1? Why do we go 1, 4, 6, 4, 1? Where did those coefficients come from? And here's the answer. It's Pascal's triangle. Everyone write it down in your notes. This triangle right here is called Pascal's triangle. By the way, Pascal's triangle has so many patterns that if I wanted to construct a lesson or a series of lessons on Pascal's triangle, it would probably be our longest unit ever. There are so many patterns in Pascal's triangle. One of them that's pretty useful is just doing the coefficients for expanding binomials, which is today's lesson. So how many of you guys have seen Pascal's triangle before with raise hands? No one. Okay. And that's my fault. I'm the math teacher. I can't blame anyone else. The way that Pascal's triangle works is you start off with 1. Technically, there's an infinite row of zeros to the left and to the right if you wanted to draw them off. And then I say, okay, 0 plus 1 is 1. I'm adding the left and right terms to get to the bottom middle term. 0 plus 1 is 1. Then you kind of have ones that go in this diagonal because it's always going to be zeros and ones. So right now we can fill in all the sides. We can say that's going to be a 1, a 1, a 1, a 1, a 1, a 1. These are all going to be ones. And again, the reason for that is technically there's an infinite row of zeros surrounding Pascal's triangle. So 0 plus 1 is 1. 1 plus 0 is 1. That's where those ones come from in the sides. But if you just want to memorize, hey, the very edges of Pascal's triangle are always ones, that's great. By the way, what I'm doing right here, making Pascal's triangle, you will have to remake Pascal's triangle on every quiz and every test. So really pay attention to do this because it's going to be asked from you guys in every quiz and test. And again, I continue the same pattern down. So the same pattern, 1 plus 1 is 2 underneath it. So my next question right here, this cell on the very far left, the blank one, what number should go in that cell? 3. Thank you, Leo. Next time, quiet raised hand. What should go in this next cell to the right of the 3? With the quiet raised hand? Sam. 3, exactly, because 2 plus 1 is 3. Someone new, aside from Leo and Sam, what should go in the far left cell right here? Ellery. 4. What about the cell in the middle? Quiet raised hands. Quiet raised hands. It's going to be a 6. and then this is going to be 4. What about the next one? What goes right here? Yes, Sam. Oh, question. The first 4 or the second 4? First 4. Good question. Who wants to answer where this 4 came from? Who can explain it? Leo, go.
I thought we were going across.
Oh, yeah, you always add down into the middle. Down to the middle. So 3 plus 3 adds a 6. 3 plus 1 adds a 4. Yeah, good question. All right. Someone that hasn't helped me build Pascal's triangle. So no Ellery, Sam, or Leo. What is the next cell in Pascal's triangle? With the quiet raised hand. Aurelio, raise your hand. Yes, Aurelio. 5. Thank you. Next cell is what? And I think you guys can probably get this from here. Just go ahead and fill out Pascal's triangle. If you want to check your work, check mine. All right, the answer key is up. Please make sure you're checking your work. All right, let's go ahead and copy down a plus b to the power of 1. That's just a plus b. So I can say that that's just a plus b. No power is needed. A plus b to the power of 2. That's this answer up here. It's a squared plus 2ab plus b squared. I hope so. We'll see. Plus b squared to the power of 3. You have a to the power of 3. Plus 3, a squared b plus 3, b squared a, or ab squared, what am I doing? ab squared plus b to the power of 3. And then a plus b to the power of 4. We just did that up here. I wish I could copy paste it, but it's a little bit too big, so I'll rewrite it. That's a to the power of 4 plus 4, a to the power of 3, b. And my b got raised too high. So b plus 6, a squared, b squared, plus 4, ab cubed, plus b to the power of 4. And I think we're gonna not have enough room either. But I think the main thing is we can see how it matches Pascal's triangle, right? The coefficients here always match the numbers in Pascal's triangle, as long as you start with the right row. And you might be thinking, well, what about row 0? Shouldn't that work? And it does, right? Because if I come back up here and go backwards and I do a plus b to the power of 0, anything to the power of 0 is just 1. And look, the coefficient here, well, the number is 1. The coefficient is 1. It matches up with Pascal's triangle still, even if we go backwards. All right, give me a fist of 5 on how well you followed Jaden's rule and Pascal's triangle rule to construct our binomial theorem. I'm seeing a 4 from Leo. A 5, a 4, a 4, 4. What are you gentlemen? 3.5. Chewy, how are you doing? How well are you following us? 3.5. Okay. Let's move on to an actual example now. So I've not done a plus b. I have substituted in a value. It's going to be 2x and y. So what's going to happen here? And I'm going to do this one for you guys. You guys are going to try to follow along the best that you can, unless you've already got this. So it's going to be to the power of 4. So the first thing that I'm going to do is I'm going to set up Pascal's triangle. I'm going to do the coefficients. I'm going to come up here to row 4, and I'm going to say, hey, the coefficient should be 1, 4, 6, 4, 1. So I come down here and I say my coefficients, and give yourself some room. 1, 4, 6, 4, 1. Those are my coefficients. Then I'm going to use Jaden's rule. Jaden's rule states I take my first term, which is 2x, and I'm going to raise that to the power of 4. And it's going to descend from there on out. So let me just work on the 2x. I'll come back to the y in a sec. I'll do these color coded too. So that 2x, I have 2x to the power of 4. Then I have 2x to the power of 3. Then I have 2x to the power of 2. Then 2x to the power of 1, which is just 2x. And then nothing, because 2x to the power of 0 is gone. That's half of Jaden's rule. The second half of Jaden's rule states that I go to the very end and I start with y to the power of 4, or you can ascend if you're careful. If I start at the very end, it should be y to the power of 4, then y to the power of 3, then y to the power of 2, y to the power of 1, or just y, and then nothing. By default, everything should be a plus sign. You only will change the plus sign to a minus sign if you have some sort of negative inside of your parentheses that are still negative after you take it to that power. And I'll show you guys an example, probably not today, as Sam kind of called out. In example number 3, we have a negative finally, so we have to be careful about. And we're basically done. We just need to simplify. So I need to ask myself, what is 2x to the power of 4? And I might have to do some scratch work off to the side. Well, 2x to the power of 4, that entire thing to the power of 4 means it's 2 to the power of 4 times x to the power of 4. And then 2 to the power of 4, that's 2 times 2 times 2. Well, 2 to the power of 3 is 8. Times 2 again, that's 16. So this should be 16. Maybe I should do it in red since it's kind of now my final answer. 16x to the power of 4 is my first term. Next, I do 2x cubed, which is 8x cubed. 8 times 4 is 32. So the answer here is 32x cubed y. 32x cubed y. And there's a plus sign still in between here. Next, 2 to the power of 2 is 4. 4 times 6 is 24 plus 24. X squared, y squared. You keep doing this over and over. 2 times 4 is 8. So this is going to be plus 8x y cubed. And then finally, plus y to the power of 4. We've combined Pascal's triangle and Jaden's rule. We are done. I boxed it. What's your question? So this 32, for example. So 2 to the power of 3 is 8 times 4 is. That's where that came from. 2 to the power of 2 times 6. I'm just simplifying. Yeah. Good question. Yes. I don't even know what that is. Oh, a front flip flat? Probably not. I bet I could get pretty close to where I landed on my head. Yeah. Oh, in example 2, I actually show us our first negative. Let me do the quick fistify though on example number 1. Where are we on example number 1? 2, a 2, a 3, 2.5, 1, 2. All right, looks like our average is about a 1.9, which is not good. So yeah, let's just do this one. Yeah. Let's do example number 2. It's a little bit different. There's just a minus sign and it turned into a 3. And it's a little bit bigger. It's to the power of 5. So again, first step, use Pascal's triangle. Pascal's triangle says my coefficient should be 1, 5, 10, 10, 5, 1. There are lots of them. So here we go. 1, 5, what is it? 10, 10, 5, 10, 10. Yeah. That's a great question. So this is a power of 4. So my second number, my second coefficient has to be a 4. If I come back up here and look at Pascal's triangle, you can see that this is going to be row 2, because that second number is a 2. So this is going to be something to the power of 2, power of 3, power of 4. That second number means what power am I to? Yeah, those are great questions. So now I'm in a power 5. So I'm using the one that has a second number as a 5. 1, 5, 10, 10, 5, 1. Those are my coefficients. I have them written down, and I have plenty of room to write in between there. All right, now I'm using Jaden's rule. Jaden's rule states I take my first term, 3x. That entire term, 3x, is going to start with the power that I'm going to, in this case, 5. So it's going to be 3x to the power of 5, and then it's going to descend. It's going to go down to 3x to the power of 4. 3x to the power of 4. And it's not just 3x to the power of 4, it's that quantity of 3x to the power of 4, the quantity of 3x to the power of 3, the quantity of 3x to the power of 2, just 3x, and then nothing. With my last 30 seconds of class, then I do the second term. And this is kind of a little bit different. I'm going to take negative y, not positive y. I'm going to take negative y, and I'm going to start on the very right-hand side and say negative y to the power of 5. Negative y to the power of 4. That's a 4. Negative y to the power of 3. Negative y to the power of 2. Negative y to the power of 1, or just negative y, and then nothing. By default, there should always be a plus sign in between here. Simplify, and we're done. We will pick this up tomorrow. There's no homework for tonight.